Welcome to using Newton's method. So just a reminder of what Newton's method was. We were to approximate a root. We were to first set x1 equal to an x value near the root. And then we were to find x sub n plus 1 by setting that equal to x sub n minus f evaluated at x sub n divided by f prime evaluated at x sub n. And then we were to stop when we reach enough decimal places. So stop when we get two x values in a row. That agree to however many decimal places. So we have the function f of x equals 1/2 x cubed minus 3/2 x squared plus 5/2 x plus 7/2. And our job is to use Newton's method to approximate the root to 3 decimal places. So we have our root here, which is very close to x equals 1, right? So negative 1. The root is close to x equals negative 1. So what we're going to do is we're going to set x1 equal to negative 1. Then x2 will be x1 minus f of x1 divided by f prime evaluated at x1. Right? So we need to know f prime as well as f. So just for our own safekeeping, we have f of x was 1/2 x cubed minus 3/2 x squared plus 5/2 x plus 7/2. And f prime of x would therefore be 3/2 x squared minus 3x plus 5/2. So if we plug in here, x1 is equal to negative 1. So we have x1 is negative 1. F of x1 would be f of negative 1. And if we plug in negative 1, we will wind up getting something, and then f prime of x1 is f prime of negative 1. And if we plug that in, we'll wind up getting something. I'm going to pause for a moment while I get those values. And so we wind up getting that f of negative 1 is negative 1. And the f prime of negative 1 is equal to 7. So we have x2 is equal to negative 1 minus negative 1 divided by 7. Or this is equal to negative 1 plus 1/7, which is negative 0.8, or sorry, this is equal to negative 6/7 or negative 0.857, So now we're going to repeat. So we will have x3 is equal to x2 minus f evaluated at x2 divided by f prime evaluated at x2. So we saw that x2 was negative 6/7. So we will find f of x2 is f of negative 6/7. And f prime of x2, we are looking for f prime of negative 6/7. So if I plug both of these in, we wind up getting negative 0.0597 for f of x2. And then if we plug it in for the derivative, we wind up getting 6.173 going on. And so now we can go ahead and solve for x3. So we have x3 is equal to, we do x2 is negative 6/7 minus f of x2 was negative 0.0597 going on, divided by f prime of x2 was 6.173 going on. And I wind up getting that this is negative 0.847 going on. Okay. So we're not quite as far negative as we were before. As I go, I'm just storing these numbers in my calculator so that you don't have to keep working with the fractions and you can be very precise. You could also always just write out the whole decimal as you can see it in your calculator. So if I store this in my calculator, then I can go through and find x4. So x4, we are looking at x3 minus f evaluated at x3 divided by f prime evaluated at x3. So again, we know that x3 was negative 0.847 going on. F of x3, we are looking at f of negative 0.847. And if I find that, I get, this is negative 2.6 times 10 to the negative 4, or negative 0.1230, and then 26. So we're getting close to a root now, right? We're very close to a y value of 0. And then if I find my derivative, the derivative evaluated at x3, we're looking at the derivative evaluated at negative 0.847, which is 6.119. So we have x4 is equal to negative 0.847 minus negative 0.00026 divided by 6.119 And if I plug that in, we have this is negative 0.8474 going on. So we actually have already found, oops, we were trying to go to 3 decimal places, right? So note that x3 was negative 0.847 ... and x4 was negative 0.847 ... And these agree for the first 3 decimal places. And so our approximation will be negative 0.847. So our approximate root will be x equals negative 0.847. So this is how Newton's method works. In an ideal situation, we only have to go out to x3 or x4. We don't have to keep going much further for finding a root. You certainly can program Excel or some other program like Mathematica to run through and do these iterations for you. But it's not so bad doing it by hand when you only have to do a few iterations of the algorithm.